So in this lecture we will talk about abstraction, pseudocode convention, and we will look at our first algorithm. So let us start with definition of abstraction and properties. So when you have to build some component of a distributed system, the first things that you have to do is to think how to formalize it in order to analyze it properly. So the first step is to define a system model, and this is what we have done in the previous lecture by seeing how to model a system, how to model processes, and how to model failure and execution. The second thing is to formalize the problem and the object using an abstraction. An abstraction is a formal object that captures the problem or the object that you want to model or the problem that you want to solve. And you do this by specifying in a way that is not ambiguous the properties that you want to be, that have to be preserved by your abstraction. We will see an example in a few moments. And the third step is to implement the abstraction using a distributed protocol. So if you want to create a broadcast primitive, for example, you have to create a protocol that performs the broadcast. And then you have to formally prove that the protocol that you implemented respect the properties stated in your abstraction. So let us start with an example, and we start by abstracting a real communication link, and we formalize. So we start with an informal description. That is, we have a link that with a certain probability loses messages, and this link that we also call channel cannot duplicate messages for an infinite number of times. So if you send a message on this link, it can be duplicated, but only for a finite number of times. And moreover, the link does not create messages from thin air. So it means that if one of the endpoints of the link receive the message, then this message has been sent by someone. It cannot be created by random noise on the channel. And this informal description is actually a sensible one because it respects many real-world links. And so let's just start by analyzing the informal description, and we want to formalize it. The first thing is the term link. So if we imagine a link has to expose two events to the upper layer are the protocols or the other things that will use the link. And one event is a request event, that is send message M to process Q. Request means that is something that is an event that is directed towards the link. And the other kind of event is an indication event that comes from the link to the process that are connected to the link, and is the deliver event. And this event delivers message M to process P. Then the second point that we analyze is the sentence that loses message with a certain probability P. And we want to transform this notion in a formal property, and we call it the fair lossy property that we indicate with FL1. And since we do not want to keep the probability in the formal definition, because working with probability is cumbersome, and we don't need it because we are not doing analysis that involves the time needed to transmit a message, we transform this property in the fair loss property. And the fair loss property says that if a correct process P, correct means a process that does not crash fail, sends infinitely often a message M to a process Q. So there is a typo here, is not message is process Q. Then Q delivers M an infinite number of times. Essentially, this means that if you keep sending messages, since there is just a fixed probability that one message can be lost and this probability is less than 1, if you keep sending the message and something will go through, but you don't have any bound on the number of times you have to send things, so you have to keep sending. This is what the fair lossy property says. Then the second sentence is that the channel can duplicate a message a finite number of times. So, and we formalize this property with the finite duplication property that we call with the acronym FL2. And this property is formally stated in this way. If a correct process P send a message M a finite number of times to process Q, then Q cannot deliver M an infinite number of times. And this is just a formalization on the fact that a message cannot be duplicated an infinite number of times. So if you just send a message M 3 times, then Q can receive at most a finite number of times. That can be 3, 6, 9, 10, 100, but he cannot receive M an infinite number of times. And the third property comes from this third sentence of our informal description that says that the link does not create messages from thin air. And we formalize this with the no creation property with acronym FL3. And this property says that if some process Q delivers a message M sent by a process P, then M was actually sent by P to Q. And this essentially says that when you receive a message, you know that this message was sent by someone. It's not possible that a message was created out of thin air. Recall that in this case, we are just talking about a point-to-point link that is a link from process Q to process P. So a link always connects only two processes, and a link works always both ways, we can imagine. So you can send from one direction to the other and the other way around. So we formalize our channel with something that we call fair lossy link. And this is just a summary of the things that we said before. And when we pictorially represent the link, we represent it with a box that has the name of the link, that is fair lossy link. And then we have two arrows on top, one that goes through the link, that is the send event arrow, and one that goes from the link to the upper layer, that is the delivery arrow. And we imagine that on top of the fair lossy link, we can have other blocks that interact with this fair lossy link using the to event. And the fair lossy link respects the three properties, the three formal properties that we have specified. Now, what we want to do, since this link is, a bit weak, it's not really powerful because you have to send things infinitely often to receive it. And we would like to create some algorithms, an upper layer that uses the fair lossy link, but they can implement stronger properties. So, but before doing that, we first have to focus on the properties, and we can do some reasoning and try to understand what is a common notions that are independent from the property that we are stating. And we have that all properties, when they are well written, they fall in two classes that can be safety or liveness. So a property is a safety property if any time is violated at time t, it can never be satisfied after t. So formally, we say that a property is a safety property if once it's violated in an execution E, there is a prefix E prime of E such that any extension of E prime also violates the property. So let us give informally, a safety property states that something bad cannot happen. So between FL1, FL2, and FL3, there is just one safety property. And one good way to try to reason about safety is to try to understand which of this property that I are above is a safety one. And the answer is FL3 is one safety property, because that says that if a process Q delivers a message M with sender P, then M was sent by P. So let's see an execution where FL3 is violated and is execution E. So I'm just stating the event of the execution because, as you can imagine, once the initial configuration is fixed, all the events, the sequence of event, the order sequence of event is enough to reconstruct the entire execution. And the problem is that once a process Q delivers a message M that was not sent by anyone, so it was not sent by P in this case because the link is point-to-point, then FL3 is violated forever. So let's see execution E. We have event E1, E2, E3, E4, and the E4 is the event that violates the property of the channel. So in event E4, it happens that process Q deliver a message M that was not inside the output buffer of process P. And when this happens, we have that we can create a subsequence E prime of E that is finite and is just E1, E2, E3, E4, and the E4 is the event that violates the safety. And then it's easy to see that in any way we try to extend the property, the execution, so we add new events to E prime, the new execution still violates the safety property because something bad did happen, and the bad things was that Q delivered something that was not sent by P. Then the other kind of property are liveness property, and the liveness property is intuitively a property that cannot be violated in finite execution. Or more formally, we can say that given a finite execution E that does not satisfy a liveness property, there is always an extension of E that satisfies it. Informally, a liveness property specifies that something good will happen. So we have safety property that says that something bad cannot happen and save our system to go in a state that are not consistent. And a state that is not consistent for our fair lossy link is the state in which a process delivers something that was not created by anyone. While liveness property ensures that if you wait long enough, if you perform an action long enough, something good will happen. And so let's do the same game that we did before. We have three properties, FL1, FL2, and FL3. And we know that, and I will say that at least one of them is a liveness property, and you have to identify which one. So stop the video and try to think about it. The solution is FL1. So FL1 is a safety property because it says that if you send a message infinitely often, it will be delivered an infinite number of times. And let's try to find something that is where this property is not satisfied, and so any finite execution. So if P send a message M and Q has not delivered it not even once by time t, there is always the hope that can deliver it at a later time. So if we take execution E where the message was never delivered between P and Q, then we can always have that this execution can be transformed in something that satisfies the liveness property, and we just have to complement E by creating an E prime that is constituted by an infinite number of deliveries. And then there is the finite duplication property that says that if a correct process P sends M a finite number of times to Q, then Q cannot deliver M an infinite number of times. And what kind of property is this? Is it safety or liveness? So it's a liveness property, and the intuition is that it cannot be violated in a finite execution. So let's say that we have an execution in which Q delivers a lot of times element M, a finite execution. Then we can always extend it in such a way that all the future events that we put in the execution are never delivery event for message M. So in this case we have E prime that contains E, and is an extension of E where we create a new event that are E1, E2, E3, and so on. And no one of these is a delivery of message M. And this means that the safety property that is, the liveness property that is finite duplication will be preserved. So just as an exercise, let's think about this variation of the FL2 property that is at most 7 duplication that says if a correct process P send M a finite number of times to Q, then Q cannot deliver M more than 7 times. And what is this, a liveness or a safety property? The correct answer is that this is a safety property, because let's take an execution that violates this property. And so in this execution, we have that the event delivery PQM happens a lot of times, so more than 7 in this case. Then it cannot be extended to satisfy this property, because once this property is violated, something bad happened, and the things that is bad is that a process delivered a message more than 7 times, And we have that once this happens, we can never recover from this, and so nothing that we'll do will satisfy the property again. So other properties, for example, are mutual exclusion property that says that if a process P is granted the resource R at time t, then no other process Q is granted R at time t. And if you think about it, this is a safety property, because if two processes are granted the same resource at the same time, this property is violated, and once it's violated, you can never recover. Then another property is not deadlock, that is a usual property, and say that if a resource R is not already granted, then eventually someone get a grant on resource R. And this is a liveness property because you can always have in the future, you can always hope that someone will get it. So it's essentially to prove that a liveness property does not hold, that an algorithm does not ensure this safety liveness property, you have to show that there exists an infinite execution of the algorithm where the property is never accessed. And so if you create an algorithm with deadlocks, then what you have to prove is that there is an execution in which there is an infinite number of steps, and this step there is a deadlock, and so the not deadlock property is violated. Another property that is always a liveness property is that is the non-starvation property, that if a process P requests a grant on a resource R, it will eventually get it. And this property is a liveness property because if a process did not get a resource up to a certain time, you can always hope that there will be something that changes and that the process can get it. There are also examples of badly written properties that are neither safe or live, or they are both. So this is one example. If a process P sends a message M to Q, then Q will eventually deliver it, and this delivery is unique. This property is mixing two aspects. The first aspect is a liveness aspect that says that if P sends a message, then Q eventually deliver it. And this is liveness property because you say that you send something and then you hope that in the future you don't bound it will the time, but something will happen and the other will deliver it. And then he's mixing a safety property also, that is the delivery is unique. Because if Q delivers M 2 times, while P just sent it once, then you have that the property is violated and is violated forever. So in this case, you should always decompose a property that you write for an abstraction is something that either safe or live. And so in this case, the correct way to write it is using two property. That is, if P sends some message M to Q, then Q eventually delivers it, and is a liveness property. And the second, if P sends a message M to Q, then M is delivered at most once, and this is safety property. So these are some homeworks that you can do, and these homeworks will help you to understand better what is safe and what is live. So let's start by looking at our first algorithm, and our first algorithm will be something that is built on top of a fair lossy and does better performance in the sense that is stronger primitive because it ensures properties that are stronger. A property is stronger than the other if property A is stronger than property B if property A implies B. And so let us go back to our fair lossy link, and we have these are the property of the fair lossy. We have our fair lossy box in below, and we want to build something above that exposes send and delivery, so it's always a channel, and this something is more powerful than the fair lossy. And the things that we don't like are, for the fair lossy property, the fact that P has to send a message infinitely often in order for a process to receive it. And the other things that we don't like is that, well, it's just the first thing, that P has to send something infinitely often in order for the process to receive it. And also the second thing we don't like behave that, okay, just the first thing. So what we want to do is to transform to create a new abstraction in which the first two properties, FL1 and FL2, are substituted by one property that is SL1, that is stubborn delivery, that says that if a correct process P sends M to Q just one times, then Q delivers M an infinite number of times. And of course, this is a liveness property, and you can understand that it's a liveness property because this thing is the combination of the two properties that we were discussing before. And to be a proper combination has to be from two properties that are the same, that means are both or live or safe. Otherwise, it will be a badly written property that mixes two aspects of our distributed primitive. And we want to create this property, this new property for our new links, the links that we will construct, and we want to keep the no creation properties, so that if a process delivers something, then someone sent it. And our first algorithm will be called the stubborn link, and is the thing that implements the two property we were discussing. So in this course, we will see a composition model of things. So the protocols that we will consider are presented in pseudocode, and the pseudocode is built using a reactive computing models, where the component inside the same process, so inside the same process we have a fair lossy component that is abstracted link, so it's not a real algorithm, it's just a link. And then we have another component that will be our stubborn link, and these two components, I mean any pair of component in our formalism will communicate by exchanging events that are, for example, in case of links, invocation of send or delivery. And then the algorithm is described as a set of event handler that will be triggered when something happens. And each handler will react to event. So if someone delivers something, then there will be an handler that reacts when a process delivers a message. And this handler is able to create new events and so to trigger other handlers. So let's go back to our stubborn link. So we want that the link exposes always the two events, the same of the fair lossy, send and deliver. And we want that it respects the two properties that are the one we were discussing before. And this is how we do it. So this is the pseudocode on the left, is using the model that I was discussing, the reactive model. And on the right, we can see the diagram of the communication between the things. So we have the stubborn link, and the stubborn link takes as input an event that is send SL, where SL means stubborn link, and it gives to the upper layer deliver SL when it has something to give up, that is a message. And for the fair lossy link, we have an event send FFL, that is send fair lossy, and an event deliver FFL. So we add SL and FFL just to distinguish when one event is directed to stubborn or to fair lossy. So on the left, we have four handlers. The first handlers, it's always triggered at the beginning of the computation. And what it does is really simple. And it says for the stubborn link, the event init, when the event init happen, what you do is to create an empty set, and this empty set is called send and is a global variable, and then you start a timer with a timeout delta. So this timer will trigger a timeout event after delta time unit. So we do not specify what a time unit is. It could be a second, it could be an hour, it could be 1 year, we don't care. And when the timeout event, so then we have the send handler, and this send handler is, we write with this formula, so we write SL, that means stubborn link, event send, and the event send has two parameters that are the process Q and the message M. So the Q is the process you have to send, and M is the message that you want to send. And when this event is triggered, what our code does is to trigger the event for the fair lossy link, so it's sending the message to the layer above, and then is putting inside the set send a pair, that is the first component of the pair is the process queue, the destination process, and the second pair is the message that you want to send. And then the last handler is the one that is triggered when the fair lossy link is sending something up. So we say when the fair lossy link FFL delivers something, and this delivers two parameters, that is the process P that was the sending process and the message M, then what you do is that you create the event deliver stubborn link, and you pass the thing to the upper layer, and you pass to it also a pair, the same pair that is the sender process P and the message M. So all the magic of the stubborn link happen in the second handler, that is the timeout handler. And essentially when a timeout happens, what you do is that you send again all the messages that are in your send buffer. And so what you do essentially is for each pair of messages sent, you trigger again the send in the fair lossy link, and then you start again the timer. So this handler, the timeout handler, is actually implementing an infinite loop if you think about it, because this is a loop that will be triggered again and again and again every time a timeout event happen, because you will harm the timer again by using start timer, and then you will trigger it again. And since this thing is triggered an infinite number of times, for any message that you have in your send buffer, you will send it an infinite number of times, right? And this means that for the property of the fair lossy link, our property FL1, that is fair lossy property, we have that a message will be sent an infinite number of times, and so it will be received by process Q, that is the one that has to receive the message, an infinite number of times. So this is actually the trick, is quite easy. And it's easy to see that stubborn delivery, that this timeout handler is allowing us to implement stubborn delivery on top of the fair lossy. And then for the no creation property is really easy. Our algorithm respects no creation because the fair lossy respects no creation. So we don't need to write any code for the non-creation property because we have the inheritance of the property of the link that we are using, that is fair lossy. So fair lossy does not create any message, and also our link for this same reason does not create any message. So as homework, try to prove in a formal way the stubborn delivery property using the fact that you have an infinite cycle in this timeout handler and that you have a fair lossy link below. So, but even with the stubborn, there is something that we don't like, and actually I don't like this sentence that is the process Q delivers M an infinite number of times, because what you want in real life, I mean, what you imagine is that you send something, and then this something is delivered, and is delivered just once, if you send something once. And we cannot bound the time you will deliver it, because we are using an asynchronous system, and we have failure on the link, so you can never know when a message will go through or not. But you want something that allows you to know that a message will eventually pass. And so what we want to do is to transform the stubborn delivery property into other property. And one property is the reliable delivery, that say that if a correct process P sends M to Q, then Q eventually delivers M. And this is of course a liveness property, because if you have an execution where Q has not received M yet, you can always extend it, a finite execution, you can always extend it with a delivery event that allows Q to process M. And then the second property is a no duplication property that says that this message is delivered at most once. And this property is a safety property, because if a process delivers a message twice, then you have done. For any extension of an execution where you deliver twice, you cannot save you anymore, so something bad happened. So now you should have the feeling and should be able to understand that both liveness and safety are useful. So let's think about a link that has only property 2, no duplication property, and property 3, no creation property, but does not have property 1. Then this link is not useful. If I just take a wire and I cut it and I give you a wire, I can say, oh, look, this wire is respecting no duplication and no creation. And it's actually obvious why, because nothing will go through the link, so you cannot deliver something more than twice, and you cannot deliver something that does not exist because it's just a link, it's just a piece of copper. And at the same time, if you have just safety property, liveness property that say that something happened, then you cannot use anything. So let's see the example in which I give you a link, and this link is really a lot of noise. It just has white noise inside, so you keep delivering messages, but this messaging is just garbage. Then it's obvious that you cannot perform any computation. And so let's look at the code to implement the perfect point-to-point link on top of the stubborn link. So we are building a stack of links. So we have the weakest one at the bottom, that is the fair lossy. Then we have stubborn in the middle, and then on top of stubborn we will create the perfect point-to-point link. That is the link that we like. It's the one that gives us the property we desire. And these things will be used again and again in the course. So we'll start from something weaker, we will create something a bit stronger, then a bit stronger, then a bit stronger. So we will go by using a refinement. And these allow you to create a nice algorithm that is really powerful and are easy to prove, because you have to just, at each time you create something a bit stronger, you have just to prove a bit more. So, and in this case, we just have three handlers. So the first handler is the initialization handler, and we always imagine that there is an init event at the beginning of the computation that is triggered and is triggered on any process. So in this case, when this event happens, what you do is that you set the you create a delivered set is a global variable, and this set is empty. Then every time you receive an event from the upper layer that is send PL, now you know why we write PL, to distinguish the event that go inside the perfect point-point link to event that go inside the stubborn or the fair lossy. What you do, you just trigger the stubborn, you just send a message to the lower layer, and essentially the only things that the perfect point-to-point link has to do, the code has to filter the duplicates that come from the stubborn link. And this is quite easy. So when you deliver something from the stubborn link, you check if this something has been already delivered, so is already in the delivery set. If not, you just update the delivery set, and then you trigger the delivery to the upper layer. So now I have to specify something that I didn't before. And essentially all the handlers in our code are always atomic. So we have that one, when the stubborn link code triggers the event deliver, SL deliver, then we have that there can be no interleaving locally. So this is easy to implement in a real system, because you just have to take a lock at the beginning of your code, and you have to release the lock at the end of the handler. And we will use it because in this way we don't have to care about concurrency inside one process. We have only to care concurrency about different process, because you have that when one process, for example, process P is executing the deliver handler, you have that process Q can execute something else. So we don't have lock among processes, but we do have local lock that can be seen only inside one process. And it's really easy to see that this code implements the property that we were saying, because for the stubborn link property, we have that once we trigger the SL send event, then we have that our receiver will trigger stubborn link deliver an infinite number of times. And if it triggers the things an infinite number of times, then we know that for the property of the fair loss, then we know that it delivered the things. And the no duplication property is really trivial to prove by using the third handler. It's easy to see that it's not possible that you pass the if m does not belong to delivered if you have already triggered perfect link deliver to p and m. So one thing that we are assuming in this property are that messages are unique. And this is something that you will see in the homeworks. So there are homeworks that will let you understand why we are assuming this and how you can implement this in a real system. And so this is the set of homeworks, and you can do it at home to understand better the things that I have said. So this ends the lecture for now.